out about the universe around us, given the fact that we've not been to very much of the universe. If you think about it, we've been to the moon, we've sent probes to the planets, that's about it really, all right? A lot of the things we talk about in astronomy, we've never been anywhere near, all right? We don't have any direct evidence for. Excuse me. Okay, so the first thing, I think, is the Earth's atmosphere. The Earth's atmosphere has a big role to play in observing the universe, all right? The largest telescope on Earth will probably be limited by the atmosphere. There will come a point where there's just no point making bigger telescopes because you won't see anything better because of the atmosphere, okay? The atmosphere, as you can imagine, is a big bundle of air stuck to the Earth by gravity, okay? It moves around, it has convection currents, I'm sure you know, it has weather, it has moisture in it, it has water vapour, other pollutants, dust, all kinds of rubbish in it. And right at the bottom here is us with our telescopes, or binoculars, or whatever, trying to observe stars out here, and obviously it has a big effect, okay? For that reason, we have developed, as you know, space telescopes that sit above the atmosphere, and as you know, if you go to the NASA website and look at any of the images from the Hubble Space Telescope, they are quite spectacular, all right? Way better than anything that you could get from the ground, okay? First thing we can observe with is obviously the naked eye, okay? And that tells us something about our atmosphere, okay? As you may know from your physics, light is just one of a huge range of waves. Light is one member of a family of waves called the electromagnetic waves, okay? You'll learn more about why they're called electromagnetic waves probably in physics in year 10, but light, as I said, is just one member of this family of waves, okay? They have the unique property that they can travel in a vacuum, okay? We don't use sound waves much in astronomy because anything outside the Earth's atmosphere is going to be out in space where there's no air, where of course sound waves can't travel. So electromagnetic waves are really important in astronomy because they're the only ones that can reach us from distant stars, okay? Light's in the middle, slightly longer wavelength. You have the short wavelength ones. These are the long wavelength ones, light somewhere in the middle. Slightly longer than light, we have infrared, okay? And everything after that is effectively radio, okay? Although through the 20th century, short wavelength radio waves became so useful, they were given their own special group and are known as microwaves, okay? If you go shorter than light, you get to ultraviolet. If you go shorter than ultraviolet, you get to X-rays. And if you go shorter than X-rays, you get to gamma rays, okay? Now, not all of these can get through our atmosphere, all right? None of them gets through unaffected, but some of them just really don't get through at all. But the good news is most of these don't get through very much. Gamma rays and X-rays are largely blocked by the atmosphere, okay? And that's obviously good news for people like us and creatures and animals and plants and things living on the Earth, okay? Light waves pretty obviously get through, all right? So you can imagine there are parts of this spectrum which are blocked by the atmosphere, okay? Not all the ultraviolet's blocked. If you think of suntan and things like that, a lot of the soft ultraviolet that's very close to light gets through, and that's why if you stay out in the sun for a long time, it murders the top edge of your skin or whatever it is, whatever you call a suntan. And, well, what other types of telescope do we see on the Earth? In fact, I had a picture here. What other types of telescopes do we see on the Earth? Radio telescopes. A famous one at Jodrell Bank. I'm sure you've seen pictures of that. A very famous one at Jodrell Bank in Cheshire, not too far from here. They obviously get through. So radio waves obviously get through, okay? And these are the two main gaps, if you like, all right? These are the two main gaps in the spectrum, all right? Because of the chemical makeup of our atmosphere, the two types of waves that get through are light, so unsurprisingly, we've evolved things called eyes that will respond to them, okay? And also radio. These are referred to as, in the electromagnetic spectrum, the optical window and the radio window, all right? If you think of the spectrum being blotted out, there are two bits that get through. There are two gaps, if you like, in the spectrum. At wavelengths around light, they get through, and at wavelengths around radio, they get through. Although this is a bit more complicated. Radio is a very long range. If we drew it to scale, radio would be like right out here. Radio waves can be as short as like a millimetre and as long as hundreds of kilometres. Okay, so it's a very wide range, but in general, quite a lot of radio gets through. Okay, and that gives you the two types of telescopes you mostly get on the Earth. Okay, with one tiny exception. Some infrared does get through up to a point. Looking at what I've just told you, you might say, well, the only type of telescope I would ever see on the Earth would be a light telescope and a radio telescope. That's not quite true. There are infrared telescopes. They're normally quite high up on mountains, but you do get infrared telescopes. Okay, they can't be at sea level. They have to be very high up, normally at the tops of mountains and things like that. But they do a reasonable job of picking up infrared from outer space. Okay, so infrared isn't totally blocked by the atmosphere, but it certainly doesn't get down to sea level. Okay, if you think about it, well, if I let you know actually, the thing that absorbs infrared is water vapour. If you've got water vapour in the atmosphere, liquid water vapour, then that will absorb infrared quite strongly. All right, that's why it can't get down to sea level. As you know, if we shut this room and turned all the heaters on and turned all the fans and stuff off, we'd eventually start getting water vapour on the windows. Are you with me? So the water vapour that's hanging in the air, because we're all breathing it out, will eventually, instead of just circulating away like it is here, if you've got a fairly warm and badly ventilated room, you've got nice cold glass. That's why if you ever see condensation on your window, sometimes wake up in the morning maybe on your bedroom window or something like that. If you've had the heating on and it's been very cold outside, then the water vapour in the room that can't really escape settles on the window and condenses back, get the word condensation, condenses back to liquid water. Okay? Now, where could you go where there is no liquid water vapour in the air? Imagine the air temperature in the room was 0 degrees. Any liquid water vapour in the air would fall out, basically, wouldn't it, as ice? Okay? That's why you get a frost. If the air temperature is very cold overnight, what happens to the water vapour in the air? It freezes, falls to the ground, and that's what you call a frost, isn't it? Okay? So it's basically the snow line, the permanent snow line. You with me? If you go up mountains, you get to a point, don't you, where there's snow all year round? So above there, you generally can get infrared telescopes. They have to be above the snow line, where the average temperature never really gets above 0 degrees. At 0 degrees C, the air around you, you can be fairly confident, is free of liquid water vapour. All right? It's that very, if you've ever been up a mountain or something, or just outside on a frosty day, the air is very cold and very clear, and it's just all the water vapour has been taken out of it. Okay? At that level, you can receive infrared. All right? Is everybody happy with that? Good. Now, we need to improve upon the naked eye. The naked eye can do so much. You can see the planets out to Saturn. You can see stars down to magnitude 5 or 6. And you can do all sorts of fantastic things with that. But if you go back to the history of astronomy thing, do you remember that one-side sheet I gave you and all the famous bits in the history of astronomy? There comes a very famous point at approximately 1609, just for dinner time. What happened in 1609 in terms of looking at the sky?
Was it the first telescope?
That's right. It wasn't the first telescope, slightly earlier, but the first person to point a telescope at the sky, not next door's army and use it for warfare and stuff. The first person to point the telescope at the sky in any kind of systematic way, Galileo, as you probably know, is the guy who gets his name on it, all right, who's quickly into print after finding his discoveries. Galileo was the first person really to point a telescope, okay? And as you know, that was a revolution. Without the telescope, would we ever really have worked out that we're going around the sun, not the sun around the earth? That's a big discussion for another day, but certainly this is absolutely pivotal, all right? I think in most modern astronomy, most things we know nowadays, we have to use telescopes for that. The naked eye is only going so far, okay? Problems with naked eye. Why isn't the naked eye, there's an eye, a scary looking eye. Why isn't the naked eye particularly good for astronomy? It's really not very well designed for astronomy. It's designed for keeping humans alive on the Earth, for spotting tigers and dinner and stuff. Yeah, there's an issue with the colour, so let's see why the telescope is an improvement. Let's look at what the problems are with the human eye. Your colour vision's not great. Even in normal light, it's not brilliant. You ask a bunch of people which shade of blue something is, everyone's got slightly different colour vision. And as we're going to learn later on, the colour of light is absolutely essential in astronomy. To be able to measure that accurately is really important. And the human eye has very dodgy colour vision. And by that I mean it varies dramatically from one person to another. Okay? How accurate and systematic is it? Not great. Okay? Also, it's not really designed for the dark. Okay? I think that's why bedtime was invented. Because the human eye is not much good in the dark, really. The best thing to do if you're a caveman, you invented fire, is just go to bed, really. Stonking around in the dark trying to hunt tigers is going to end badly, all right? There are other animals on the earth that have much better night vision than we have. So it's not brilliant in the dark. In particular, what happens to your colour vision in the dark?
It goes.
Yeah, it just disappears, basically. So it's not really designed for this sort of thing, okay? It's not a very accurate measure of brightness, but a more important one is to do with the human eye's, this is a word you need to know, aperture, all right? If you've been fiddling around with cameras trying to take pictures, you'll know all about aperture. It's the size of the hole. So if we're doing top technical words, it's as simple as that. That's a small aperture for a camera or an eye, and that's a bigger aperture, and that's an even bigger one, okay? Aperture is really important. Aperture is the size of the hole that lets in the light, okay? The human eye, it's a few centimetres, isn't it? It's not really very big. What does that mean? It affects two things. Astronomers tend to call this the light grasp. It's a simple idea, it's how much light's getting in. The light grasp of the human eye is relatively low because it has a small aperture, okay? And there isn't much else you can do about it. If you don't get much light into the system, then it's very difficult to do anything about that afterwards. You can't recover something that you never had, okay? And the other one is it affects the sharpness, okay? Which I guess nowadays we would refer to as the resolution, okay? So the human eye is not great because it's not good for looking in the dark. Fundamentally, the hole in the human eye, the aperture, what's it called, the pupil? Yeah? The pupil of the human eye isn't very big. So, not much light grasp. That's fine as long as you don't want to look at dark and dim things. Oh dear. All right. It's great in this room, but there's tons of light around. The light grasp is perfectly adequate. You can see all corners of the room perfectly well. Okay. But if you start looking at dim things, faint things, things that aren't very bright, things that are set against a black background, this is going to become an issue. Okay. Second thing, it affects the sharpness or the resolution. And because we now live in the computer age, I'm sure you all know what a high resolution picture looks like and a low resolution picture where it's all crunchy and made of blocks and things like that. There's a limit on how sharp an image you can see because of the hole at the front. Okay? So what we need to do is basically to increase the aperture. Alright? That's the fundamental issue with telescopes. There's no point trying to magnify something if you haven't got enough light in the first place. Alright? Many people think the most important thing with a telescope is its magnification. If you've seen the big blue one we put in the quad for open evening, have you seen that one? Great big telescope. First question everybody asks is, what's the magnification? I can't remember, to be honest, because that's largely irrelevant. The important thing is the hole at the front is about the size of a large dinner plate. All right? Yeah? So the point is it gets lots of light in, so you can then magnify the image. Magnifying the image, if you haven't actually got very much light going in, is a waste of time. It's not going to work. Okay? So it's not magnification. I would say top of the list with telescopes is aperture. If you buy an astronomy magazine, look at the second-hand ads. They say things like 10-inch Meade reflector, 16-inch Cassegrain, what's his name or something. Every time, every advert leads with the diameter of the hole at the front. Are you with me? If you're buying a telescope, that's the most important thing. Look at an advert for a telescope manufacturer. The 8-inch telescope costs this much. The 10, the 12, the 14, 16-inch telescopes, the price just goes up. All right? There are things you can see with a 14-inch telescope you simply cannot see with an 8-inch because it just doesn't get enough light in. Okay? Magnifying it definitely comes second. All right? Which I'm sure if you stop many people in the high street, they would think of it the other way round. But there's no point setting up a big magnification, which you can do easily by changing the eyepiece, if you haven't got enough light in. So aperture is the key thing. Galileo's telescope, probably about that sort of size, I think. I think it's in a museum in Florence or something, you can go and see it. The lenses are about that big. Yeah? So it is a step up from the human eye. Okay? It has a bigger aperture. All right? So we've increased the aperture from the size of the human eye to, I don't know, you can look it up actually, I think, what was it, 6-7 centimetres, something like that. Okay? So we've increased the aperture. What will that mean is it will give, well, this is basic common sense. If you make the hole at the front bigger, you get more light in, all right? You get a brighter image, and you also get a sharper or higher resolution image, okay? Not by a massive amount, and it's just one of those quirks of fate, really. I often like to think about, here's the human eye. What things are just beyond the human eye? What things, if the human eye were just a little bit bigger, would you be able to see? And very famously, of course, it is the moons of Jupiter. And the other one is the phases of Venus. Sometimes, you all see Venus? It was in the morning recently, isn't it? Have you ever seen it? It was rising in the morning before the sun. You were in bed, aren't you? It has been rising in the morning before the dawn with another planet. I can't remember which one it is, but Venus looks absolutely spectacular, this bright dot. And sometimes it's a full Venus, and sometimes it's a crescent. Do you remember we looked at Galileo in his drawings? Sometimes it's a crescent, sometimes it's a full. Can you see that with the naked eye? No, you just see a dot. But how much bigger would your eye need to be in terms of the hole in the front, the pupil, to be able to see the phase of Venus? Not very much. So Galileo was a lucky man in many ways. He happened to just increase the aperture of the human eye with his telescope by just enough to tick these two. How important are these two discoveries in terms of the geocentric, heliocentric debate? Absolutely fundamental, all right? So these just fall exactly. If Jupiter was 10 times further away, if Venus was 10 times smaller, we might still be arguing over it. Don't know, probably not. Okay? So, that's the idea of this type of thing. Now, this type of telescope is called a refracting or a refractor. Okay? You should know from your physics, refraction is to do with lenses. Now, all telescopes have lenses in. What we're referring to is the one that lets in the light. The lens at the front that lets in the light has a special name. It's called the objective. All right? So the objective of Galileo's telescope was a lens. The thing that you point at the stars that collects the light was a lens. Okay? And for that reason, his telescope is called a refractor. Okay? And ever since then, people have been making larger and larger refractors. Okay? But particularly in astronomy, where it's all about dim things. Generally in astronomy, you're looking at things where there isn't very much light. So you're not fussed for magnification, really. You're interested mainly in light grasp or aperture. Okay? Now, this process kind of carries on, as you might imagine, and we could go through, if you want to, in the handout, there's a couple of drawings of Saturn that show you this idea. I always think a nice example is an example of Saturn's rings. Okay? First person to look at Saturn was Galileo with his small telescope. He thought it was a planet with ears. He thought it was a planet with two large moons either side. He really wasn't quite sure what was going on. Why? Because he was looking with a telescope like this, and he was getting a relatively low-res picture. Okay? If you go on a little bit later, so there's Galileo. Go on a little bit later, there's a guy called Christian Huygens, one of the people we think may have been responsible for developing the telescope in the first place. He used a slightly larger aperture. What did he see, something Galileo never worked out, was the fact that Saturn has rings. Okay? A bit later on, somebody else looked with an even larger telescope, and they realised that Saturn had rings around it with a gap in it, called the Cassini division. You had a big dark gap in Saturn's rings. Now, why did Giovanni Cassini, who wasn't Italian actually, he's French I think, despite his name, Giovanni Cassini, why has he got his name on that? Was he a better astronomer than Galileo? No, he just had, it's all about aperture. He was looking through a telescope that had a lens about the size of a decent saucer, all right? And he could see, with higher resolution, he could see the division, okay? And it just goes on. There's the Encke division. There's another one in there somewhere, all right? There's another division somewhere called the Encke division, okay? Not discovered by Mr. Encke for some reason, discovered by someone else. But anyway, the point was, whoever discovered that was looking through bigger aperture, all right? A lot of the discoveries in astronomy, why did certain people make these discoveries? Why is Christian Huygens the first person to write about the rings of Saturn? Giovanni Cassini wrote about the Cassini division, Mr. Encke wrote about the Encke division, whatever. It's just because they had larger telescopes, all right? Larger telescope gives you sharper pictures and brighter pictures, okay? Up to a point, this is where we'll stop this afternoon, there comes a problem, okay? First of all, if you think about a refracting telescope, it's the sort of classic telescope we always expect astronomers to use. And when we have the big blue telescope out there in the summer, that everyone wants to look along the axis of the tube, but in fact you look in the side. You actually look in the side of them, okay? This type of telescope is a refractor. It's got a big lens at the front that collects the light. It's got a little lens at the back which focuses it for the human eye. The problem becomes that this lens needs to get bigger and bigger and bigger, all right? Making enormous pieces of glass about the size of this room, okay? And then putting them at the top. Can you see? It's an engineer's nightmare. The gigantic, heavy, glass is technically liquid, isn't it? So it's got some stability issues and things. This huge, great piece of glass has got to go at the top of the tube. The tube has to then be able to move and track the Earth and stuff like that. You couldn't make something more top-heavy, could you? And in fact, just manufacturing, because glass is technically liquid, if you make an enormous glass lens exactly to shape, when you pick it up, because you can't support it in the middle, when you pick it up, it sags slightly. Do you follow? Refracting telescope, I shouldn't think there's any actual astronomy being done seriously by professional astronomers in the world now that it's done by a refracting telescope, because you simply can't make the lenses that big. The objective lens, the big one that goes at the front to collect the light, can't actually be made that big. And you end up by making a device which is completely and utterly unstable, all right? Having made the lens, getting up the top of the tube and keeping it there in a stable way and being able to move it around becomes really difficult, okay? That's the first problem. The second problem is the problem of false colour, okay? False colour has a very grand scientific name. It's called chromatic aberration. Now, chromatic aberration is a bit of a problem. Here's your giant lens at the front of your telescope. Here's a nice beam of white light coming in from a distant star. Now, if you look at the top of a lens, the top of a lens is essentially, apart from the slight curve, the top of the lens is a little triangle of glass. What do little triangles of glass do to white light? It does a lovely job, which is great for people who want to study it. It breaks them up into colours of the spectrum. Yeah? So what do you actually image? You end up with an image. Do you get a nice white dot? No, you get a red, orange, yellow, green, blue, indigo, violet splodge next to each other. There could not be, to be honest, you can get lenses for telescopes and cameras which suffer from chromatic aberration. To be honest, if you keep bright lights away from the edge of the frame, if you want to take a picture of your family on the beach or something, as long as the sun isn't in the frame and there's no bright bits around the outside, you could happily spend a lifetime taking perfectly good pictures with it, all right? But what are we doing in astronomy? We're always looking at little bright white dots of white light, and we really don't want them to appear as anything other than little white dots, all right? So false colour, chromatic aberration, happens in all optical devices that have lenses, because, I know, let's make the side parallel, then it won't do it. What's the problem with that? What if I make the sides of this piece of glass parallel? Because then it's not a prism, is it? Yeah, it's not refracted, is it? Exactly. It would just go straight through. I've just invented the window. Light, what does light do in a window? It goes straight through, doesn't it? Yeah? Because the sides are parallel. What happens in a lens? The sides are curved. And so you get the, as you said, refraction, the change in direction. So what can you do about it? Not a lot, really. Camera manufacturers, the reason the guys who take photographs at Man United behind the goal, their lenses cost £10,000, £20,000, £25,000 is because they will have in them elements of glass which are engineered using all kinds of expensive chemicals to make a glass that does this very little. Are you with me? That's not easy to do, and it's not a total solution, but it makes the thing extremely expensive. A guy who spent a long time trying to solve this problem was a gentleman called Isaac Newton. Okay? He spent a long time trying to solve the problem of false colour and realised pretty quickly that there was no solution, really, unless you can find a glass that doesn't do it, and that isn't really very possible. So he invented a telescope that doesn't use a lens to collect light at the front, it uses a mirror. Okay? That type of telescope is called a reflecting telescope. Okay? And all serious astronomy nowadays is done with reflecting telescopes. It has two advantages. One, you don't have this size problem. When you hear about the Keck telescope where the mirrors are like 30 metres across or something like that, you think, crikey, that's a third the size of a football pitch or whatever. How on earth do they do that? Is they don't use a lens. They don't have a big lens at the top of a tube. They have a big mirror at the bottom. All right? And that solves many of the problems we had here. Having the heavy bit at the bottom of the tube, basic engineering, makes it so much easier. And what's the big advantage of a mirror over a lens in terms of supporting it? Yeah, you can put something on the back of it, can't you? In fact, some modern telescopes have little thruster things, little hydraulic rams on the back. So if the mirror goes out of shape, the computer can actually push the mirror back into shape. Okay? Can you do that on a lens? Well, you can't, can you? Because you can't block the hole, all right? And the second thing is you get rid of false colour, all right? Section 5 is on observing the universe, all right, how we find out about the universe around us, given the fact we've not been to very much of the universe. If you think about it, we've been to the moon, we've sent probes to the planets, that's about it really, all right? A lot of the things we talk about in astronomy we've never been anywhere near, all right? We don't have any direct evidence for. Excuse me. Okay, so the first thing, I think, is the Earth's atmosphere. The Earth's atmosphere has a big role to play in observing the universe, all right? The largest telescope on Earth will probably be limited by the atmosphere. There will come a point where there's just no point making bigger telescopes because you won't see anything better because of the atmosphere, okay? The atmosphere, as you can imagine, is a big bundle of air stuck to the Earth by gravity, okay? It moves around, it has convection currents, I'm sure you know, it has weather, it has moisture in it, it has water vapour, other pollutants, dust, all kinds of rubbish in it. And right at the bottom here is us with our telescopes, or binoculars, or whatever, trying to observe stars out here, and obviously it has a big effect, okay? For that reason we have developed, as you know, space telescopes that sit above the atmosphere, and as you know, if you go to the NASA website and look at any of the images from the Hubble Space Telescope, they are quite spectacular, all right? Way better than anything that you could get from the ground, okay? First thing we can observe with is obviously the naked eye, okay? And that tells us something about our atmosphere, okay? As you may know from your physics, light is just one of a huge range of waves. Light is one member of a family of waves called the electromagnetic waves. Okay? You'll learn more about why they're called electromagnetic waves probably in physics in year 10, but light, as I said, is just one member of this family of waves. Okay? They have the unique property that they can travel in a vacuum. Okay? We don't use sound waves much in astronomy because anything outside the Earth's atmosphere is going to be out in space where there's no air, where of course sound waves can't travel. So electromagnetic waves are really important in astronomy because they're the only ones that can reach us from distant stars. Okay? Light's in the middle, slightly longer wavelength. Here are the short wavelength ones. These are the long wavelength ones, light somewhere in the middle. Slightly